Okay. Hi everyone, my name is Long Chen and I will be presenting our recent work whose practical multiple TFAT. This is a joint work with Keson Park and Yongsu Song. So let me first introduce you the notion of fully homomorphic encryption. So it is an encryption scheme which allows us to perform arbitrary function evaluations of encrypted data. So it can be applied to lots of applications such as privacy preserving machine learning or PSI or PIR. Usually FAT is used for two-party setting, the key owner and the evaluator, but it can be extended to a multiple-party setting. So there are two types of multiple-party setting FAT, namely multi-key HE and the threshold HE. So multi-key HE has a key structure of the concatenation of its party secret keys, and threshold HE has the key structure of the summation of each party secret key. So those two types have their own pros and cons. So for example, multi-key HE is dynamic and its key setup phase is independent, but the time and space complexity is dependent to K. And threshold HE is static and its key setup is interactive, but its time and space complexity is comparable to single key schemes. In this talk, I will be only focusing on the multi-key HE. So there have been few theoretical studies on multi-key HE, such as LATV12 or CM15, etc. But they are mostly based on GSW scheme, which is not very performant. And also they don't have any implementations at all. And then there are two practical schemes, CCS19, which is based on TFAT scheme, and CTKS19, which is based on CKKS and BFW scheme. So both of them have causality complexity. And then recently, both of them were improved into a quasi-linear complexity in KKR SS22 and this work. Now, let me start by describing the TFAT scheme. So it is an FAT scheme which supports bit operations such as NAND or so it has two types of secret keys, RW secret as a vector and RLW secret T. So to encode a single bit, -1 or 1, we can simply multiply Q over 8 to the message. And to decode it, we can simply check if it is positive or not. Now, to encrypt an encoding of a message, we firstly sample A from a uniform distribution and E from a small distribution and compute B equals minus inner product of A and S plus mu plus E modulo Q. Then we obtain a TFAT ciphertext of BA. To decrypt this ciphertext, we can compute B plus inner product A and S modulo Q. Now let's see how one can evaluate a binary gate homomorphically in TFAT scheme. So for two input ciphertexts C1 and C2, we firstly compute a linear combination of those two ciphertexts with respect to a Boolean gate we want to evaluate. So for example, if you want to evaluate an AND gate, you can compute 8 over Q minus C1 minus C2. Then this is a valid ciphertext which encrypts the result of the gate evaluation. But the problem is that it may contain a large noise. So it should be followed by a costly operation called bootstrapping, which reduces the size of the noise for further evaluation. So the bootstrapping in TFAT consists of two steps called the blind rotation and key switching. Since the most challenging and costly parts of the bootstrapping is blind rotation, we will be only focusing on the blind rotation in this talk. Now let's see what happens in blind rotation. So we have an input ciphertext C equals B comma A, such that B plus inner product AS is the message, the encoding we want. So we firstly scale the ciphertext from the modulus Q to 2n. Then what we want to do here is to homomorphically decrypt the ciphertext of the exponent of a monomial. Since we are working on a ring where x to the n plus 1 equals 0, the mod 2n arithmetic is naturally supported of the exponent. So what we do is to pre-assign the coefficients to a polynomial called the test vector, so that the constant term of test vector times x to the b plus inner product as is q over 8 times m. So we can bootstrap the input ciphertext by computing TV times x to the b plus inner product AES and extracting the constant term. So what we need to do is homomorphically multiply x to the AISI to TV times x to the b iteratively. So this is the main bottleneck of TF-AT bootstrapping. So let's get into the details of the multi-key TF-AT. So in the setup phase, each ith party samples LW secret SI and RLW secret TI. Then the multi-key secret is given as a concatenation of each party's secret. So for example, LW secret S, the multi-key LW secret S is a vector of length Kn, which is a concatenation of the secret keys Si, and RLW secret T is given as a concatenation of those RLW secret of each party. Note that this multi-key secret is never revealed to any party, and each party I holds their own ith key and never reveals it to other parties. So the ciphertext has the form, a very similar form to the single key H scheme. So the C is given by a vector of Kn length Kn plus 1, where B plus the summation of AI in a product of AISI modulo Q is an encoding. So to decrypt it, you can just simply compute B plus summation of AISI. So in CCS 19, we perform blind rotation very similarly to the single key blind rotation. So we homomorphically multiply monomials x to the Aij, Sij to the test vector iteratively. But note that Sij is a secret information which is only known to the ith party that should be encrypted on the ith secret key Ti. So what we need here is to a multiplication algorithm which can multiply between a multi-key ciphertext and a single key ciphertext. So the authors constructed a new algorithm called the hybrid product in CCS 19. So it can multiply a multi-key ciphertext and a single key ciphertext. It has the time complexity of OKN. So since the LWE ciphertext for multi-key scheme has the length of Kn, we require Kn hybrid products. So it makes the overall time complexity of blind rotation OK square n square. Note that it has a k square term. The time is scaled quadratically as the number of the parties k grows. So what we want to do in this work is to mitigate this time complexity to linear. So the underlying idea of our work is that we can perform blind rotation party-wisely and in a single key manner, and you can merge them together. Since a single key blind rotation has the time complexity of O(n) square, since we perform those blind rotation in a single key manner k times, the overall time complexity will be OKN squared. But the challenging part is that there is no non-homomorphic multiplication algorithm between multi-key and a noisy, in other words, not fresh single key ciphertext. If we perform blind rotation party-wisely, then it will never be fresh anymore. So we need a new algorithm that can multiply between multi-key ciphertext and a noisy single key ciphertext. So we constructed a new algorithm called the generalized external product, which can compute a multiplication between multi-key ciphertext and a not fresh generic single key ciphertext. And so we can construct a new faster blind rotation algorithm with time complexity Kn squared. Now let's get into the details of the generalized external product. So we have three inputs, the multi-key encryption CT and a noisy, not fresh encryption C of mu on the secret TI, which is the secret of ith party. And we have a fresh encryption Relin key of TI on the secret TI. So what we do here is that we can multiply C to each index of CT, then we can obtain a multi-key ciphertext, which encrypts M times mu what we wanted. But the problem is that the key is now changed to a tensor product of 1TI and 1T1.tk. So we have to change the key back to 1T1.tk. So let's rephrase the resulting ciphertext here is a concatenation of two vectors x and y, where x corresponds to the key t1.tk and y corresponds to the key ti times 1 t1.tk. Then we can multiply Welling key using hybrid product to y and add it to x, and the key is changed back to 1 t1.tk. So at the first step of our algorithm, we utilize a single key multiplication k times, and in the second step, we use hybrid product, which has the time complexity of kn. The overall time complexity will be OKN. Now let us construct a new faster blind rotation algorithm. So firstly, we compute the monomial x to the inner product AISI for each ith party in a single key manner. And then we multiply them to x to the b times test vector iteratively using the generalized external product. Then in the first step, since we perform blind rotation in a single key manner, k times the overall time complexity of the first step will be kn squared. And in the second step, since we utilize the generalized external product k times, and generalized external product has the time complexity of kn, the time complexity of the second step will be k squared n. So in total, the time complexity will be OKN squared plus k squared n. In practice, we use a parameter where k is much smaller than n, so we can actually ignore the term k squared n. So we achieve a quasi-linear complexity of OKN squared. Now, this new blind rotation algorithm has two advantages over CCS19. So firstly, note that we compute those monomials in the first step independently. Those first step can be algorithmically parallelizable. And also it is key computable. In CCS19, since we have to perform hybrid product, we need a special kind of structured single key encryption. But instead, since we use the blind rotation in a single key manner, we can just use a single party scheme public keys for our blind rotation, just with an extra Welling key. Now let's see the high-level overview of CCS19 and our algorithm. If you see there, in CCS19, the monomials have to be multiplied to the test vector sequentially, but in our algorithm, we can just independently compute monomials and merge them together at the end of the computation. So these are the timing results. As you can see, we achieve 4.4 times speed up with the parallelization and 52.6 times speed up with parallelization for 16 parties. And in CCS19, they don't even have a practical parameter for 32 parties due to the slow performance of the quadratic complexity algorithm. So if you see the graph, the difference is more clear. So as you can see, our algorithm shows a linear growth with respect to the number of parties, and CCS19 has a quadratic growth with respect to the number of parties. Thank you for listening, and these are the GitHub repos to the implementation of our algorithm. So one is in Juliet and one is in Go. Thank you for listening. Yes. It's not really directly translatable because threshold case has completely different kind of key structure. So in TFA scheme, we usually use a binary key. Then the threshold case gives some kind of not binary case anymore. So that case, we have to use another algorithm to really resolve that. So. But is it still So it requires some kind of multiplications between the public keys. So I wouldn't say that it will be the exactly same algorithm. So it's kind of different. Thank you.
Okay, I have another question for you. You have in the about two different kind of flavor of homomorphic encryption. One is MKFHE, one is the homomorphic. Could you talking about from the application perspective? Can you talking about how the different application of two kind of schemes?
In multi-key HE scheme, you don't need to like interact with other parties. So if you just download the common reference string, then you can just publish your public key and they will do the computation. But if you are using threshold HE, then you need to know which party will be joining the computation, and you have to interact with those parties. So also multi-key HE is dynamic, as I told you earlier. So if during the application, if another party will be joining or you don't want any more communication, then multi-key HE will be a better choice. But if you don't really care about the communication, and if the timing is really important to you, then you should use threshold HE.
Okay, thank you. And do you have any questions? Some more questions? So let's start with the speaker again. This the slide, the title of the talk is about faster harmonized THEW bootstrapping using real homomorphism. It's about Gabriel Micheli, Lu Yun, Daniel Chen, Adam Sua, and Micheli will give the talk.
Thank you for the introduction. So, as was just said, I'm not going to repeat the name of my co-authors. This was joint work with Intel and UCSD. And so the work I'm going to be talking about today is about faster amortized few bootstrapping. So as we know, FHE schemes are kind of divided into two families of schemes. We have bitwise FHE schemes where messages are encrypted bit by bit. And this is, for example, the schemes that are TFHE, and thankfully the talk before described TFHE quite well. We have another family of FHE schemes, which are BGB BFE schemes. These are word-wise FHE schemes where a full message or actually multiple messages can be encrypted into a ciphertext. And the interesting thing about this kind of FHE world is we have different trade-offs for these different families. If we look at latency, for example, few TFHE is much faster. We had a first work which claimed to do bootstrapping in less than a second, and this was optimized to less than 0.1 second. BGP BFE is much slower. But then if you look at amortized time, for example, the situation is reversed, where because the message space for BGP BFE is much larger, then we have an amortized cost, which is much smaller than for few TFHE. So our work is going to focus on amortized bootstrapping in the context of few ciphertext. So we're looking at an algorithm that is going to bootstrap and few ciphertext at the same time for a very small overhead. So the work that we did is actually inspired by some previous work from Sorel and Michancho, which was published in 2018, where they did present a first algorithm for amortized bootstrapping, which was theoretically very promising, but the main barrier to their algorithm was a very impractical algorithm due to a very high overhead. So the work that we did in this paper was to obtain better, but like somewhat similar asymptotic amortized costs, but with a much smaller overhead. So let me start by briefly going over what bootstrapping for LWE ciphertext looks like. So bootstrapping is basically a homomorphic evaluation of a decryption circuit. So what does this mean? If we take the simple decryption of an LWE ciphertext, and this was mentioned in the talk before, basically we have an inner product between the ciphertext AB and we have a secret key S. And following the inner product, we have usually a rounding operation. Now, what does it mean to homomorphically do that? Well, we start by having some bootstrapping keys where this time we encrypt the secret key. So we encrypt every coefficient VI of our secret key. And then in order to bootstrap a ciphertext AB, we are going to compute an inner product, but this time the inner product between A and the secret key is with an encrypted secret key. So here we're talking about a homomorphic operation, in particular a homomorphic scalar multiplication. We also need to do a homomorphic addition and also the same like a rounding operation, which is done homomorphically. And assuming that all these operations, we are able to do them homomorphically, then the result of this bootstrapping should be the encryption of the message M. Now, in the original Few paper presented by Duca and Michancho in 2015, the bootstrapping had a kind of a particular aspect where the homomorphic description was done in the exponent. And I'm not going to go into too many technical details here, but the idea is that the encryption of the secret key here was the encryption of a monomial this time. So encryption of X to the ZI using the RGSW encryption scheme. And the rest of the bootstrapping follows the same structure. We do have an inner product, we do have a rounding step, but this time everything is computed in the exponent. Now, the main limitation of LWE bootstrapping is its cost. So if we think about homomorphic multiplication per message, this is at a cost of O of n. And so if we want to bootstrap n messages, then we obtain a quadratic cost, which for practical FHE parameters, this is impractical, infeasible in practice. So the motivation of this work is to focus on amortized bootstrapping to reduce the cost of this operation. And so amortized bootstrapping means that we're not going to bootstrap a single message, but we're going to bootstrap n messages at the same time. And in order to do this, we use the ring LWE structure. So the ring structure, the ring decryption, instead of the LWE decryption. So the process is very similar. We start with a ring packing step, where this time we're considering, say, D LWE ciphertext, and we pack them into a single ring LWE ciphertext. And then we have an inner product, we have a rounding. The important thing to note here, excluding all the kind of mathematical details, is that now we are dealing with polynomials. So if we have an inner product, we're talking about an inner product between a polynomial structure instead of a vector structure. So in our work, we focus mostly on this inner product. This is the main step which differs from previous work. And as you can see here, we have this inner product between A and Z, where this time we're talking about polynomials. So the whole goal of this work was to see how we can do an efficient polynomial multiplication homomorphically. So the goal is to compute A times Z, two polynomials, and Z in this case is encrypted. We have an encryption of our secret key. Now, we all know that a fast way to do polynomial multiplication is to use the fast Fourier transform. So in order to do a fast Fourier transform homomorphically, there's a bunch of operations that needs to be done homomorphically. Not only addition, which was used in the previous work, for example, but we have subtraction. We also have multiplication by some elements, which are called twiddle factors, usually, which are powers from the root of units. So if we're able to do all these operations homomorphically, then we can exploit this FFT algorithm in order to have a fast and more efficient polynomial multiplication. And we obtain something of the order of n log n instead of a quadratic cost for multiplication. Now, going back briefly to the previous work, one of the main bottleneck of the algorithm was that the algorithm from Michancho and Sorel used RGSW registers, which only supported homomorphic addition. And so in order to do what I mentioned before, these homomorphic subtraction or scalar multiplications, then there were either tweaks that they presented in their paper, but they did not exploit the FFT algorithm. So they had a promising asymptotic complexity in theory. In practice, there was a huge overhead. So the key observation that we do in our work is that we can actually efficiently perform homomorphic scalar multiplication with the RGSW registers. And because we're able to do these scalar multiplications using automorphisms, then we're going to be able to use the FFT algorithm in order to perform the polynomial multiplication. This gives us a better asymptotic complexity and also a smaller overhead. So I'm going to give a very, very brief description of FFT. The one thing I want to focus on in this slide and also in this talk are the homomorphic operations that are required and how do we compute them. FFT is a complex algorithm. There's a lot of variance, a lot of parameters. So keep in mind that this is just a simple description, and obviously optimizing the variance of FFT, optimizing the parameters, this is all things that were taken into account in the paper. So the general idea of FFT is we have kind of two steps. We evaluate degree n polynomials at some roots of unity. And then once we're in this FFT domain, we're happy we can do a component-wise multiplication, point-wise multiplication. So the evaluation, the first step basically resembles a remainder tree. And again, it's a very hand-wavy description of FFT. But what matters is that at each layer of our tree, we're doing some reductions of some polynomials modulo other polynomials. And the operations that we have in a layer of a tree would be what is written in parentheses. So we can see there's some summations between elements, and we have these AI that are also multiplied to roots of unity. So these zeta to some power. And for pointwise multiplications, we're going to have similar operations. So in order to perform this algorithm homomorphically, because obviously we know how to do this algorithm in plain text, we will need basically two operations. So in this slide and for the rest of the talk, usually when there's a square around a value, this means the value is encrypted. So we're going to need two operations, a scalar multiplication, where we have a ring element times an encrypted value, and then we have addition of two encrypted values. Now, what's important to note here is that the feasibility of these homomorphic encryption is going to depend on the encryption scheme that is being considered. And so in our work, we were mostly going to use gadget RLWE, but we are going to need RGSW for one of these operations. So a little bit more on these homomorphic operations. So going back to what I said for the P bootstrapping, where everything was encoded in the exponent, well, we do the same thing. So for the message encoding that we have in our work, a scalar value is going to be encoded in the exponent, which means that we are mapping this value to the monomial x to the. Now, as I just said, we're going to use two registers, RW prime, so the gadget RLWE version, and RGSW. And so going back to the two operations that I want to do, we have scalar multiplication. To do these scalar multiplications, we're going to use automorphisms on gadget RLWE. And for addition, we are going to between So I have no idea what time it is. Oh, there's time here. I have no idea when I started. So for the sake of time, I'm going to skip the description of these two operations, but very briefly, ring automorphisms, application of ring automorphisms to an RLWE ciphertext is going to be basically applying this automorphism to every single component of the RWE ciphertext. And this is usually followed by a key switching in order to have the RWE message encryption with the automorphisms under the secret key SK and not the secret key with the automorphism. And same for the multiplication. The details of the multiplication between an RLWE and an RGSW ciphertext are described in the paper, but this is one operation that we know how to do. And also note that in this talk, I'm not going to talk much about error growth, which is something really important for FHE, but the whole analysis of the error growth of these algorithms is in our paper, if anyone's interested. So this operation is important because it allows us to multiply two ciphertexts, which in the exponent, as I said before, will act like an addition. Now, another important contribution that we introduce in our work is a scheme switching technique. And the reason why we need scheme switching is because, as I said before, some of these operations, the feasibility of these operations depend on the scheme that we're using. So for example, for multiplication, addition meaning multiplication in the exponent, we are going to base ourselves on RGSW ciphertext. And so in our algorithm, we will use the scheme switching technique in order to go from an RLWE prime ciphertext to an RGSW ciphertext in order to be able to perform this multiplication. And one of my last slides is an example of how one of these operations work. So hopefully this will clarify some of these all these operations. So now going back to the Fourier transform, which is what we want to do. So we want to, taking even another step back, we want to compute this polynomial multiplication in order to homomorphically decrypt our circuit. And so the FFT-based multiplication algorithm is pretty standard. So we have A and we have Z. We can compute the FFT of A. A is then in plain text. We can compute the FFT of Z is this time encrypted, because we recall that we have encryption of our secret key. Once we are in the FFT domain, we can do a component-wise multiplication. So we have FFT of A times Z, and then we need to do an inverse FFT in order to recover A times Z. So this basically summarizes what I just said. We have various operations that needs to be done, point-wise multiplication, FFT, inverse FFT. But what matters here and what I want to convey in this talk is that we are able to do every single operation that is needed for these different steps. So this operation performed kind of summarizes what I said in the previous slides, where we do have the encryption AI, an encrypted coefficient times this zeta j, which is the equivalent to scalar multiplied in the exponent, and this is done using automorphisms. And below is just an example of a summation of two encrypted data, which we're doing with two steps, a scheme switch in order to have an RGSW ciphertext, followed by this multiplication that now we know how to do. So this is the example that I was talking before. So this illustrates what could happen at one layer of the FFT in the evaluation step. This is just to illustrate kind of the sequence of these operations that we're able to do. So the goal is to compute what is at the very top, have hidden by the audio setup. So we have a sum of encrypted values. Some of them are multiplied by these twiddle factors. This summation, this formula can be rewritten in different forms, just like in the second line of the slide. And recall that the AI are RW prime ciphertext. So for example, this could happen in our FFT algorithm. This is a computation resulting from a polynomial being reduced modulo another polynomial. So how are we going to do this? Well, we can start with the left side of the formula or the right side of the slide. We have A3, which is encrypted. We need to multiply it by something. How do we do this? We use automorphisms. And this gives us this A3 times theta. Now we want to add this to A2. Again, we have two encrypted values. A2 is an RWE ciphertext. And so in order to do the multiplication, we first do a scheme switch, and then this allows us to do the multiplication, this time between an RGSW ciphertext and an RLWE prime ciphertext. And so the computation goes like this in sequential operations using automorphisms, multiplication, and scheme switching to have the correct scheme. So this kind of illustrates the main operations that are used in our algorithm. Now, how much time do I have left? So this example kind of concluded the description that I had of our algorithm. So again, I put aside a lot of the technical details. In particular, something that does not appear in my presentation is the analysis of our algorithm, the complexity, the error growth, etc. But the details are on the paper. Now, one thing that I wanted to mention kind of to conclude this talk was kind of the scene that we have for amortized bootstrapping nowadays, because especially last year, we had quite a few very interesting papers that came out slowly improving the state of the art for amortized bootstrapping. So starting with our work at the very beginning of last year, which was concurrent to another work from Guimarães, Carrera, and Van Leuven, where they outputted an algorithm which uses very similar techniques to ours. There are some technical differences. Again, I will refer to their paper or ours for some description of their the technical differences. But the main thing that I wanted to say here is that both these algorithms improve the asymptotic complexity from the original work from Michancho and Sorel. There are, we have smaller overhead, but still we're far from having a practical algorithm. Now, a little later during the year in Eurocrypt 2023, Yu and Wang presented two papers that were one after the other, one using the previous work, which also significantly improved the asymptotic cost of amortized bootstrapping. In particular, so in the first paper, they introduced this new kind of algebraic framework based on the tensoring of three rings. And in their second paper, they combined this kind of new algebraic structure with the structure of the Chancellor-Sorel paper to obtain a very good asymptotic complexity. So as you can see, O of 1. But again, if you dig a little deeper into the parameter choices that they have, it does not seem very practical. So a great theoretical result, but perhaps not really practical. And then in AsiaCrypt of 2023, as I was saying before, a lot of things happened last year for amortized bootstrapping. So not the same set of authors, same last names, but different people. They actually improved, again, amortized bootstrapping, both theoretically, but also in practice. So their paper has 7 millisecond in their title, if you've seen it somewhere. So they exploit a scheme switch between a few TF-HT ciphertexts, but they also utilize VFE ciphertext in their paper. So great practical performance. Their work is hard to compare with the other line of work, especially because they use a super polynomial modulus as opposed to a polynomial modulus like the rest of these papers. So basically, where do we stand for amortized bootstrapping? There's been a lot of work. There's a lot of ideas that came out last year. New methods, I mean, ours, for example, but also the more algebraic structured papers that came out later that year. But there doesn't seem to be yet like a defined winning candidate for practical performance in particular. So we still have this performing gap between amortized Q and BGP BFE, which we're trying to reduce, but we're still not there yet. One last thing that I wanted to mention for the end of the talk is efficient implementation. So I'm mentioning this because in particular, our work, we use prime cyclotomics instead of power of 2 cyclotomics. And this is not something that is well implemented or optimized in FHE libraries. So we've been asked multiple times what would be a complete running time for our algorithm, et cetera, et cetera. It is a question that was hard for us to answer because part of the inefficiency of our scheme could result in part, I'm not saying all of it, in the fact that for general cyclotomics of power of 2, we don't have efficient implementation in common libraries that we could use. So one future work direction would be to incorporate more of these non-prime, non-power of 2 cyclotomics for these new schemes that are appearing. And thank you so much for your attention.
The skill multiplication. I think 0 times A minus C. Why don't we put A that's doing a sum of C max.
Wait, so the question is, why don't we so the scalar, so let me back. I might not have understood the question, but basically the scalar multiplication is a ring element A times a ciphertext, an encrypted, something encrypted, right? So in order to do this, because we're working in the exponent, right? So in order to do this, we can apply an automorphism. So it's kind of doing an homomorphic exponentiation. That's what's happening with scalar multiplication in the exponent. And so automorphisms allow us to apply this exponentiation to every single component of our LWE ciphertext. And then it follows the scheme switching because if you look here at so we're applying like pi t to like every monomial, also if you're next to the t, so we do a scheme switch to go back to the original secret key.
So A is not a ring.
A is a ring element.
Oh.
Okay, that was sorry, could have been a shorter answer.
That's the speaker again. Now we come to the last talk session. The title of the talk is about instantiation on level for homomorphic signatures from type assumptions. The paper from Brown and Gray, so then Usu, and Gray will give it talk.
Thank you. And Oh, sorry. Thanks for the introduction. Okay, so let's get started. I'm starting with some preliminaries, but basically, well, you all know what FHA is. We have two encryptions. We can compute encryptions of the sum. We can compute encryptions of the multiplication and arbitrary circuits. Here it has RET2, but this can be readily extended. And correctness is preserved up to some noise bound. So that was easy. And as we have seen in the previous talks, we are always interested in bootstrapping, where we, in order to control our noise, we are going to have a first ciphertext that is an encryption of the secret key of the FHE. And we're going to use that to evaluate the decryption circuit, which will allow to obtain an encryption of the original message, but with refreshed noise. And the noise is refreshed because of the rounding step. And we're not yet into the model of what fully homomorphic signatures are, which is what our target for this talk is. But we're going to first think about what would be like, what do we want? So basically, if we have signatures of some message, one M1, M2, I want to be able to compute the signatures of the addition. I'll take the multiplication in the circuit. And we already know, based on GDW15, how to construct this based on lattices, so SIS. And again, but constructions are leveled, so we do not have unbounded number of levels. And the reason for that is that bootstrapping is hard for signatures. Basically, we do not have an equivalent of what it means to encrypt a secret key. If we sign the secret key, then we are leaking it, so no security. And also, like, even when you're thinking about what would you do to reduce the noise, well, actually, like, evaluate what function. It's a question mark as well. So fundamentally, there is a problem here into getting to an unbounded number of levels. And we want to overcome this. And we're going to do that from a more complexity theory perspective rather than, well, an actual practical implementation that you can deploy. But maybe that comes later. And now that we kind of know what we want to have, we're going to look at the model, which is a bit more complicated. So we need to take some time for this. We can have key generation as for a normal signature. But when you're looking at the circuit, because you want to verify it, ideally, you would not want to go through all the steps in the circuit. So usually the model here is looking at the processing function, which is kind of like squashing the circuit down into a verification key for the circuit. Yeah, this is like a pre-processing stage. And then we have our two, Alice and Bob. Alice decides to sign some messages M1 to MN. Sends this to Bob, and Bob can basically do two things. It can evaluate signatures on circuits. And it can also, I mean, this Bob is arbitrary. There are multiple Bobs out there. If it has a signature, it can verify using the verification key for the circuit if this Y is actually a computation of the circuit on M1 up to MN. So this verification is always relative to the original messages that were signed. And we want succinctness. Of course, we want that the size of the evaluated sigma star should not be too large. Otherwise, we could just put all the original signatures, and like we could verify, but it will not be very interesting. And also, we want that the size of this verification key is short as well, and that yeah, as I said previously, computation it can be really dependent on your circuit. Your circuit can be something like look some machine learning algorithm that you want to run. Some classifier can be fixed, so everyone knows this verification key is what we want. And the final property I'm going to talk about is composability. So basically here, I'm saying that I want, once I have two signatures that correspond to evaluations, these are homomorphic signatures, I want to keep doing that. I want to be able to apply circuits again and again and again and again. So formally, basically, you can have some K circuits, C1 to CK. Here I have signatures of the outputs of these circuits. And I want to be able to evaluate some function F to obtain an evaluated signature on this new circuit here. And basically, this circuit is, of course, the composition of the circuits from before. So these are the inputs, and this is this new function that we are applying. And conceptually, we want to do this again and again. So want this G can become the input again of some other evaluation procedure. And this property is actually one of the hardest properties to achieve. But all of these properties are properties that FHE inherently has. So FHE can always continue to evaluate homomorphically. So what is the security? So we have an adversary and a challenger as usual. I'm very proud of this job. So the challenger will generate the verification key and the secret key. The messages are being chosen by the adversary. And once it gets the signatures, the adversary tries to compute and evaluate the signature, pick a circuit C star and some target value Y star. And we want that this signature is valid, but it does not correspond to an evaluation of the circuit on the original messages. So it's a valid signature, it passes, but actually it doesn't authenticate the value of the circuit evaluated on M1 up to M. This is our unforgeability definition. So one thing you could think of is this bound N here, a limitation in the model, because, well, the challenger always signs this M1 up to Mn. This N is determined by the verification key. And what is done in the literature is to consider labeled versions here, where you can add arbitrary labels to the data sets that you sign. And basically, these labels are just arbitrary bit strings. And we know how to remove that, but we need to use random oracle model techniques, and that adds an additional assumption. This is just a note. Maybe there is a way to not use random oracles here, but this is an open question. So looking a bit at the state of the art on fully homomorphic signatures, a paper from 2013 showed how to do this for max. So in this symmetric key setting, the depth was unbounded, but it has some limitations. The security was only up to a logarithmic number of verification queries, where this N is the number of messages that you sign. And also this is not so much of a limitation. Then GVW15, which is our reference, managed to achieve a leveled scheme that has a bounded depth. It's bounded at setup time based on ISIS. It can get rid of this bound using the random oracle model. And then we also have another work from last year that basically achieves unbounded depth quite efficiently compared to our work. Their assumptions are more closer to standard assumptions, so like pairing assumptions or neural lattice assumptions. And the only limitation is that the circuit width is bounded. And also, I didn't write it here, but there's also a limitation on how you can compose circuits. You can only compose them sequentially, but it's a very nice work. And also, another thing you can do is to use snarks. If you use snarks, you can get an unbounded number, unbounded depth, but conceptually, then you have to rely on knowledge assumptions or the random oracle model. And we are interested in only using falsifiable assumptions. So avoiding knowledge assumptions for now, at least for this work. It's always good to have multiple options. So what we have is unbounded depth, and we're using very heavy machinery. So we're using obfuscation, we're using one-way functions, we're using fully homomorphic encryption and non-interactive zero knowledge. And if you want to get rid of the bounded number of messages, we're going to have ROM as well. But I would say this is the main result here, the first. So let's talk a bit about falsifiable assumptions, why it's an interesting topic. So falsifiable assumptions are assumptions that satisfy two conditions. Condition number one is that the assumption should be able to be modelable as an interactive game between the adversary and the challenger. And the condition two says challenger should be able to decide efficiently whether the adversary has won the game or not. And this is very relevant. And just as a note, this means that the adversary winning probability cannot be too small. So this is here I mean asymptotically smaller than 1/polling, because then the challenger will not be able to decide efficiently if the adversary has broken the assumption. And this, in general, conceptually, philosophically, we are really interested in this kind of assumptions because these are the assumptions that we can invalidate with cryptanalysis. These are the assumptions that we can exhibit attacks against, as opposed to knowledge assumptions like the knowledge of the street log assumption, where we can't really say, look, there's an attack against it. So now that I convinced you that falsifiable assumptions are nice, let's look at our first building block, which is indistinguishability obfuscation. So obfuscation, as it's in previous talks, it says that the functionality of a program is hidden, but it can still be executed. And the formal definition is that you have two circuits that evaluate the same function. So they really evaluate in the same way for all possible inputs. And once you have that and you pass them through an obfuscator, they look computationally indistinguishable. And you might think, look, this is very boring because why would you want to hide the things that compute the same function? So they compute it, but they compute it in a different way. That is what is being hidden. And it turns, I mean, we know that everyone knows, I think, I don't know, that actually I/O is extremely powerful and it implies almost every sufficiently complex primitive in cryptography. And a recent line of works from like in the last several years has built I/O, and it's huge number of citations. You have to look at the paper that basically has built I/O from falsifiable assumptions. So if we manage to base our fully homomorphic signature on I/O, then we are also implicitly basing it on all these potential candidates that have falsifiable assumptions. And now we're going to look at our main tool that I'm going to give you a flavor of the construction. The main tool for these obfuscation techniques is that you're using puncturable pseudorandom functions. So you have a program, you have a hard-coded PRF key, K in it, you have a randomness, you generate some randomness, which is the evaluation of the PRF at that point X, and then you use these points for some other primitive that comes inside the program afterwards. So the way you do it, you're going to puncture this key at some point X star, where you're going to use security. You're going to have to hard-code the key there, the value of the PRF there, because now you cannot evaluate it anymore using the key. If you're evaluating the program at X star where you punctured, then you have to use this hard-coded value. Otherwise, you're going to evaluate the circuit of the PRF. And you use the coins for some other primitive. You do another hybrid where you replace this hard-coded value now using the pseudorandomness of the PRF with a random egg, and then you're using the security of the primitive now because now you have that these coins are actually uniformly random. So that's kind of conceptually the main tool for puncturable PRFs. So now we can look at an initial idea. Let's say we take some digital signature scheme. DS is like a normal vanilla signature scheme. And we say, look, we'll try to build a fully homomorphic scheme by signing a message using this. And let's try to construct an evaluation circuit for the NAND gate, which is it can imply like the entire like all functionalities. So for example, if you have your message and two signatures, you could compute the evaluated message and compute the randomness, and then let's say we want to use this randomness as the secret key for this digital signature scheme. And then you can add in the circuits that, look, I only want to output the signature with this actual randomness if the inputs are valid. There are many problems with this approach. One of them is like there is no way to predict where to puncture. The adversary really has a lot of power. It can choose. It can also choose. It can choose the circuit. It can choose the value which it forges. So unless you have to predict a lot of things, you could predict X maybe by guessing, but even then you're going to have issues because whatever was output here, it would be potentially refed as an input to this program. So it's extremely hard to prove. Also, in the model, the evaluation circuit doesn't really get the circuits. It doesn't really know for what circuit the signature assigns M. That is only available to the verification circuit, not to the evaluation one. We only know that the signature is valid for this message, but we don't know what is the circuit that corresponds to the message with respect to the original initial messages. And even if we manage to puncture by guessing, and we manage to make this SK here really random, we still need to remove it from the program somehow in order to use the security of the scheme. So the idea I gave before doesn't really work yet because we still need to remove it somehow from the program for this particular case. So the solution is to use statistics, so non-interactive zero knowledge proofs, which, just as a quick recap, you have a common reference train. You're making some we're proving a statement in an empty language. They only have one message, and both parties have access to the CRS. And we can formalize this by saying that the CRS is in two modes. You can have a binding one in which You have soundness, so the CRS is generated along with an instruction trapdoor. You can always extract the weakness. And you can have a hiding one where the CRS is in a simulation mode, and you can use the simulation trapdoor to generate fake proofs. The two modes are computationally distinguishable. So let's look at the second idea. The second idea is to have a ciphertext, which is a fully homomorphic encryption of the message. And then to make an ISIC proof that, look, indeed, what is encrypted here is an actual encryption of the message that I want to sign. And then the advantage for this is that the CTI component, the FHE component, is going to be homomorphic by default. So let's look at how our NAND evaluation circuit changes. This thing is exactly the same. We have our evaluated point. We have the randomness that we generate on the evaluated point. And now we are going to use this randomness, instead of using it as a secret key of a digital signature scheme, we're going to use it as the generating random string that is fed into the setup of the NISIC CRS. Then we can compute an FHE eval on the original ciphertext. And if the proofs that are fed into the circuit are correct, then we can compute a new proof for the new ciphertext. So now more problems appear. Problem number one is, how do you compute this proof? You need a witness for it. You can't just compute it. And that is the randomness of the evaluated ciphertext. One idea is to use it to extract it from the proofs, from the proofs in the signatures, by using the extraction trapdoor of the NISIC. And if you have it, then you can compute. Then you can take the randomness from each one of them, from sigma 0 and sigma 1, and you can use the randomness evaluation algorithm of the FHE scheme to predict what is going to be the randomness of this evaluated ciphertext here. So that's how we get the witness in order to compute the proof. But the problem is that now anyone can sign, because you can just pick your ciphertext, you generated it yourself, you know its randomness, and you can compute it. You have the witness, and you can compute an ISIC proof. So that's bad. The signature is not secure. But there is a fix to this, and the fix is to take this n ciphertext, so generate n ciphertext, push them into the verification key, and keep the randomness for yourself. Don't publish it. So now no one knows what the ciphertext encrypt. But when you sign, you're going to generate the proofs that the ciphertext actually encrypt the messages that you want. And this obviously, so now we fix the problem that no one can sign, not anyone can sign, but we have another problem, because at the verification time, when you compute the verification key, we do not know what messages are going to be signed later. And this is where the scheme becomes quite nice. What we do is that actually the ciphertext that we publish as part of the verification key are going to be encryptions of 0. We're going to make a hybrid argument, and then switch to a hybrid where they actually encrypt what is supposed to be there. And because they are encryptions of 0, you're going to use the simulation trapdoor in order to compute these proofs. And for those of you who work with NISICs, now you're maybe already seeing a problem with this. We're not going to get into it, but the problem is that, well, I'm going to use in my evaluation circuit the extraction trapdoor in order to get my randomness to compute the next proofs for them, for what is output by the evaluation circuit. But at the same time, here I need the simulation trapdoor in order to compute these proofs for the original messages. This is not possible with NISICs. You cannot have both simulation and extractability at the same time, but it is fixable. For details, I refer you to the paper. And there are a lot of other technical problems. This brings me to the end of the talk. So let's conclude. We built a fully homomorphic signature scheme that is based on I/O, FHE, and NISICs. And it is the first one that achieves the following 3 properties at the same time. We have an unbounded number of levels. We can arbitrarily compose circuits, and we are based on classifiable assumptions. And if you want to abstract out a minimal set of assumptions for this, basically you could use sub-exponential I/O and sub-exponential pairing assumptions, or sub-exponential I/O and sub-exponential LWE. And this is it. Thank you for your attention. And I'll be happy to answer your questions.
which way you use IO can do
Oh, by witness encryption.
only have a solution. So it's kind of
That's interesting. I mean, I don't know exactly, like maybe it's plausible. Like potentially you could like somehow like have some original things in your verification key, and then you sign if you know, only if you know like the charter for it. But I would say it's a very like the witness for it, but I would say it's a very incipient idea, like to actually being able to like I'm going back to the model slides to be able to have all these properties that you have composability of circuits and you have like this nice security game, right? And like nice functionality. I think like taking the idea and implementing it would be quite. Yeah, definitely. It's a I would say major open problem. At least for me, I would like to see that. A smaller open problem, I don't know, for students, I guess, would be to get rid of this bounds without using random workers. That would be also nice, I think.